Hello. Okay, I think it's time to start. So a few announcements first. So this Friday will be 梅竹赛, so we will have no class. But the homework still need to be turned in, so you can turn in the homework outside to a box outside. Turning the homework to a box outside the TA's office, or if you scan it somehow or type it up, I think you can also email your homework to TA. Yeah? And I think next Tuesday is also a holiday, it's Ba. So we'll have a lot of holidays for these 2 weeks. But anyway, we'll still have homework for what we teach today. So let's keep the homework schedule going, but it will probably be a smaller homework. So homework this week also out, and it will be due next Friday. Okay. Any question on the scheduling? No? If not, then yeah, let's review a little bit. So last time we kind of rushed through this very fast. So it's about, this time we said there is some interesting thing about periodic complex exponential in discrete time. And the thing is, in discrete time, the frequency are kind of periodic. So because how the discrete time, because how we are only sampling at the integer value for discrete time, so we can only really see frequency in a 2 pi interval. And I guess we can jump around. And those are illustration of this effect. So for continuous time, if you increase this omega naught parameter here, your signal just keep oscillating faster and faster, and it will get more dense. But for discrete time, because you are only seeing the signal in the integer intervals, so when you are oscillating too fast, your signal actually goes back to what they look like with the slower time. So for example, here you can see when you are oscillating at this omega 0 equal to 2 pi, then that's sense you got the same signal as not oscillating. So your frequency is only meaningful in an interval 2 pi. And the highest frequency one, well, this is not very well defined, but as we'll cover very soon, because sometimes it's not even periodic. But the thing that seems oscillating more fastest is at pi. Okay. And let's jump a little back. Okay. And we just talked about how it's not even periodic for a lot of omega naught. And indeed, if you solve the equation and you want to see, so you have this discrete time signal of e to the j omega naught n, and what is period, what is its fundamental period, then you solve this equation that e to the j omega naught n equal to 1, and you find out that the omega naught n should equal to some integer multiple of 2 pi. So you have this relation, the important thing that omega naught divided by 2 pi should be m divided by n. And you know m is an integer and n is an integer. So you know for your signal to be even periodic, this omega naught divided by 2 pi must be a rational number, because this is integer and this is integer. And then we can solve for fundamental frequency. Fundamental period, then fundamental frequency from this relation. So if you move things around, then you see that your fundamental period should be, well, this period should be m times 2 pi divided by omega naught. And so fundamental period will be the smallest positive number that can satisfy this relationship. Okay. And you think about how to satisfy this with the smallest positive number, then you see that, well, first your m and omega naught need to have the same sign, otherwise it's not positive. So if you have a negative omega naught, you want a negative m here. Then you just find the smallest m. So this is going to be a rational number, so something divided by something. Then you find like the smallest possible denominator here and put it as m here. So that will be your fundamental period. Then from fundamental period, you can calculate fundamental frequency. And you just go by definition. Fundamental frequency is going to be 2 pi divided by n. And that will be omega naught divided by the smallest possible n. Okay. And any question? And let's see. So, and we go through those 3 examples. So when you calculate your big N, or not really big N, when you calculate your 2 pi divided by omega naught, so in this example is 12. So you know your fundamental frequency is just 12. And here you have your 2 pi divided by omega naught. Is it 2 pi divided by omega naught? Yeah. Yeah. Excuse me. Yeah, your 2 pi divided by omega naught. So your 2 pi divided by omega naught equal to 31/4. Then you want to multiply this with some small m to make this n an integer. So you just times this 4 and you get n equal to 31. Okay. And for this example, you have your 2 pi divided by omega naught is 12 pi. And this is a irrational number, so this is not even periodic. Okay. And we have the result here. Okay. So that's a quick review. And here is another summary of the result here. And I think, yeah. So here, they are saying this relation between omega naught and n is different word. So they are saying for finding the smallest m, you want m and n to not have any common factor. Okay. And I think they are missing the minus sign thing. So just remember, if omega naught is negative, you want m to also be negative. Okay. So this is a table you can look up. It's also in the book. Okay. So no question, then let's go into an easy example. So we have a signal that's sum of 2 of those complex exponential in discrete time. So e to the j, 2 pi divided by 3n, and 3 pi divided by 4n. So the fundamental period of this, fundamental period of this, and the fundamental period of this. So is there someone that want to just give us all the answer here? Give some time to think. Okay. If not, then let me walk through this. Okay. So as we say, what we want to calculate is this 2 pi divided by omega naught. And because we want to use this n equal to m times 2 pi divided by omega naught. So we just calculate 2 pi divided by omega naught for those 2 signals. Okay. And okay, so you have this omega naught equal to 2 pi divided by 3. So for this one, this 2 pi divided by omega naught is 3, and for this one is a over 3. So that's elementary school math. Okay. And from here, then you should be able to read the fundamental period for those 2 signals pretty easily. Okay. So this is just an integer. So you know for the first signal, its fundamental period is just 3. Okay. For the second signal, it's a divided by 3, and this already has no common factor between 8 and 3. So you know the big N should be 8 here. And but if you want to walk through this slower, then you will read the whole text, the word text here, and it basically says, well, you see that you shift your signal to x of n plus a over 3, then it will be the same. But you are a discrete time signal, so you cannot shift by a over 3. So you try to shift more, so you shift by 16 over 3. But that's still not an integer. Then you shift another a over 3, then you go to x of n plus 8. Then now this is a good shift because 8 is an integer. So you know that this x of n to x of n plus 8 is the same signal, and this is a very discrete signal. So you know the fundamental period is 8. Okay. And okay, so that's the first 2 questions. The first one is 3, and the second one is 8. And then the next question is what's the fundamental period of those 2 signals adding together? Well, then that number should be a multiple of 3 and also multiple of 8. And so that's the least common multiplier of 3 and 8, and that's just 24. And here we are implicitly using something we didn't quite say. But okay, so let's do this kind of basing of jumping all the way. So we have a little correction here. Okay. So we are doing something we didn't state explicitly. So I will do it now. Around here. Okay, so this line. Okay. So we are saying if the fundamental period is t, then all the integer model of t are also period of your signal. And the thing is, the converse is also true. So if your fundamental period of t, then only those integer multiple of t can be your period. So if you have like a 2.1 t and like a pi times t, those are not going to be period. So this is actually a if and only if relationship. Only those things are the period of your signal. Okay, and similarly for n. And we have a homework problem that don't totally prove this, but give you give you an idea of this. So you are going to prove in your homework that if your fundamental period is t, then 1.5 t is not your period. Is not a period, and you can basically do a shift. And so I guess a hint from homework. You should be able to show. You should be able to say that if 1.5 t is your period, is also a period, then 0.5 t is going to be a period, but that's not possible because t is the smallest period. Okay. So that's a homework showing that this converse. Okay. And you can, if you are still thinking clearly, then you see that this is what we implicitly do here, because we are saying 3 is the fundamental period of first signal, and 8 is the fundamental period of the second signal. So the period for both signal needs to be a multiple of both 3 and 8. Okay. Okay. Someone is nodding. That's good. Okay, so that's that. And finally, let's wrap up this periodic signal thing with harmonic-related discrete time exponential signal. Okay, so this is similar to the continuous time, but we also got this frequency only from 0 to 2 pi thing right back. So the idea is that we want to find all the periodic exponential signal that has a common period big N. So they should have this 2 pi divided by big N here, and then times integer multiple k here as is omega naught here. And so its frequency is kind of this k times 2 pi divided by big N, or k times, I guess we didn't use omega naught here, but anyway, yeah, k times 2 pi divided by big N. And but for k too big, this frequency will just right back to itself and give you the same signal. So, and how big that is actually a very cute number. So you can calculate that. If you go from k to k plus big N, then that'll give you the same signal as k. Okay. So there are only n distinct signal, and you can get. So there are actually preference you can choose, depending on your question. But you want to pick basically n consecutive numbers. So usually you pick from 0 to n minus 1, and those are your harmonic signals for common period big N. And obviously there are some other choice. So some maybe say n is even, maybe you pick like minus n over 2 to like n over 2 minus 1, something like that. But you want n consecutive numbers for those omegas as your harmonic signals. And here we reuse the graph before to give you an idea of those harmonic signal. So we can actually use those graphs for harmonic signal for n equal to 16. Right? So n equal to 16, then 2 pi divided by n will be this 1 over 8. Okay. So this 1 over 8 is 2 pi divided by 16. Sorry. Pi over 8 is 2 pi divided by 16. And so k equals 0, you have a signal like this. But also this is Palatine cosine, so it's a little different from this because we are having complex exponential here, and here we're plotting cosine omega naught t. So this is only the real part of this complex exponential, and well, but because it's hard to plot complex numbers, so let's just look at the cosine part. So n equals 0, your harmonic will look at this, so it's a constant function. Then k equal to 1, so 1 period is 16, so it's about this. Okay, so k equal to 1 is this 1 oscillation. Then k equal to 2, you have 2 oscillation, and when we jump a lot, we jump to k equal to 4 and k equal to 8. You can see this is still the phase is oscillating one, and there should be like 8 oscillations in 16 dot because it's one up down up down up down up down. And then k equal 12. K equal 12 actually look the same as k equal 4 because only look at the real part, so that's a little annoying, but you can kind of get the idea. So just imagine there is an imaginary part that is the negative sign of this. And yeah, then k equal to 14 and k equal to 15, that looks a lot like k equal to 1. And back to k equal to 16, that actually equal to k equal to 0, etc. Okay, so those are pictures of discrete harmonics. So I guess you need to remember that there are only n distinct signals. Okay. So any question? If not, we'll change to other topic. Okay, pretty fast. Okay, now change to totally different signal. No more exponentials. But there are very useful signal for signal analysis. The unit impulse function and the unit step functions. Okay. Well, let's just go into a definition. So we'll start with discrete unit step and the unit impulse because they are easier to define. And you can see it's a very simple function. So unit impulse function is, unit impulse function is this function that has 1 at n equals 0 and 0 elsewhere. It's one of the simplest functions. Okay, and obviously you can time shift it. So if you time shift it to the right by n naught, then this impulse at 1 will become, instead of placing it at 0, you will placing it at n0. Okay, so this should be pretty simple. Okay, and yeah, it's a 1 at 0, or when you shift it, it has a 1 at n0, and it's 0 or otherwhere. And unit step function is also very simple. So it's 1 at everywhere, greater or equal to 0, and 0 or elsewhere. And you can also shift it. Then you will start to be 1 at n0. Okay. So those are the definition. Okay. Now, this trivial thing is those two things we are talking together because they are actually related to each other. Okay. So you can think of this unit impulse as the difference between unit step, and this is a very picture relationship you can see. So you have delta of n that has this 1, 1, 1, 1, 1, 1, 1 starting from 0, and if you shift it by 1 to the right, so you have u of n minus 1, there will be 1, 1, 1, 1, 1 starting at this 1 location, and you just take a difference of those two. Then everything cancels out except at 0, and you will let this unit impulse. Okay, so this proof you can just see from picture, or if you don't like pictures, then you can run through the definition and see the same thing as a picture. Okay, and then less obvious thing. So I actually find this a bit confusing, but anyway, you can also turn this relationship backward. So it's kind of, you do the inverse of differentiation and you get the integration. And anyway, you do this, you kind of invert this thing, then you can get your unit step function as a sum of unit impulse function. And here this is confusing because you need to check there's this extra variable you are summing over. So you need to check what you are summing over and where you put your n. Okay. And anyway, so here this is like integral. So the n for your unit step function is on this upper bound of your summation. And you are summing another dummy variable m. So you are summing over delta of m from somewhere to from minus infinity to your n. And yeah, you can it's kind of like integral, and you can view this on a line. Okay. And when you draw these pictures, you need to be careful about, once again, you need to be careful about what variable you are summing over. So here we are summing over m. And so delta of m will be this unit-imposed at m equal to 0. And you are summing over from minus infinity to your big N. And now you just consider a case of where is your big N. And if your big N doesn't touch this delta, then it should be 0, as your unit step function should be. And if your n is greater or equal to this 0, so you touch this delta, then it will be 1. Okay. So this makes sense. Okay. But, okay. So why do I keep talking about be careful about the dummy variable? Because we are going to do a change of variable to another dummy variable to make this more confusing. I guess this is kind of more intuitive way view of this. Okay. But anyway, so if you do a change of variable, so you define k equal to n minus m, then then you will actually get rid of this big N here. Okay. So you do a change of variable. So k equal to n minus m. So here you have n minus n equal to 0. And here you have n minus minus infinity, which equal to plus infinity. And k equal to n minus m. So m equal to n minus k. Okay. So you have this summation. And but now you are summing over some dummy k, but your n is not in the limit of your summation anymore. Your n is just in this delta function n here. And you can switch the upper and the lower bound of a summation because the ordering of summation doesn't matter. So this u of n is summation of k from 0 to infinity delta of n minus k. Now you can have an interpretation of this, or kind of like a reverse of this. So basically we are saying our u of n is this function that has 1, 1, 1, 1, 1 starting from 0 to infinity. And we can view each of these peak here as the delta function, right? So delta of n minus 0 is just this first peak here, so k equals 0. Then you have k equal to 1 is the delta shifted by 1. And k equal to 2 is the delta function shifted by 2 steps, etc. Okay. So this is saying that your unit step function is a summation of a whole bunch of delta function placed one by one. Okay. And so that's one way to look at this. And you can also, so I guess hopefully this is not too confusing for you, but you can also look at this as a summation over k, and it's another integration over this delta thing. Okay. Anyway, so those are delta function and the unit step function. The definition should be pretty clear, and they have those relationships. And why would we like them so much? Because they can let you, we can use them to analyze our signal by doing this thing. So if you multiply your whatever signal x of n with your unit impulse function, the delta of n, then that will just give you your value of your signal as times 0. Times your delta function, because it's 0 everywhere else, so it only depends on your x of 0. Okay, so this kind of lets you sample out your signal at x equals 0. Okay, because it's 0 everywhere else, so it's just this delta signal at n equals 0. And similarly, you can sample at a different point. So if instead of delta of n, you have delta of n minus n0, then you see you multiply those two things together, you get x of n0 times your delta. So you can pick out the signal by doing this multiplication. Okay. Any question on discrete time, unit impulse and unit step? If not, then let's go to continuous time unit step and unit impulse. And this is more annoying to define because, because it's continuous time. So let's first define unit step function. And so you want your function to jump at one place because because continuous time you just want to jump at some time. So you want your unit step function to jump at t equals 0, so you define it as this. Is 0 when t is less than 0 and 1 when t equals to 1. And here you already see something funny here because this is basically undefined when t equals to 0. Okay? And I think some places would like to define this t equals 0, you have u of t equal to 1 over 2, but we don't really need that, so let's just leave this undefined here. Okay. And what's even funnier is this unit impulse function here. Okay. And here we are not giving a definition, we just like you see. So it's basically a function that's 0 everywhere, but infinity at t equals 0. Okay. Yeah. So we kind of want it to be a 1 at 0, but that's not good enough because we want to have it integrating over will be a 1, so this needs to be infinite high. And this infinity high, we describe it with this funny arrow here. Okay. And so this is a unit impulse function. And if you go to other courses, maybe some physics course, this is also called a delta function, mainly because we use delta here. And if you want to be mathematically rigorous, say if you look up Wikipedia, then Wikipedia will say this is actually not a function. It's called a distribution or something. But anyway, we still call it delta function or unit impulse function because that's easier to say. Okay. Okay, so let's get a definition of this weird delta function first. Okay. So we define the unit step and unit impulse function as the limit of two well-defined function. And writing down the equation is not too helpful, so let's just define those two functions as a picture. So we have this u delta function, which is 0 when your t is less than 0 and 1 when your t is bigger than delta, and just linearly interpolate between 0 and delta. Okay. And and your u of t will be the limit of u delta when delta goes to 0. So your slope just gets higher and higher until it's very straight. Okay? So this is the unit step. And this delta of a triangle, as we say, we want it to have like area 1. Kind of like in discrete case where you summing over it, you give you a 1. Now you integrate it over it, it should give you a 1. So you should have this really narrow thing. So it's 0 everywhere except between this 0 and the triangle. And the height is 1 over triangle. So the whole area of this rectangular is 1. And as delta gets smaller and smaller, this will get thinner and thinner and higher. So the delta function is the limit of this delta subtriangle, and you see the height will go to infinite and the width will go to 0. So actually 0 everywhere except it's infinite height t equal to 0. But the point is when you integrate over it, the area stay as 1. And also you see that you can check easily that this signal is the differentiation of this signal. And that should be k plus. We think that should be stay true when you take the limit of triangle go to 0. Okay. So I guess this is something that we can spend on time to look at. And any question about the definition? So that's a weirder thing. I don't know. Do you guys learn this in your calculus class or no? Okay. I don't quite remember what people teach in calculus, but guess not. Yeah, but anyway, those are delta functions and unit state function. And it's a pretty funny definition, but it's what it is. It is infinite height and 0 width, and but as delta goes to 0, the area keep the constant 1. And okay, next slide. So as you might probably expect, this is a thing I keep saying, and it's a relationship we want to have between our unit state function and delta function. That is, when you integrate over your delta function, and you will get back your unit state function. So if you have your delta function here, then you integrate from minus infinity and see do you pass it. So when you integrate past it, then you will get 1, because when you integrate over your delta function, you should get a 1. And so that gives you a unit state function on this upper bound of your integral t. Because when t is less than 0, then you are integrating over 0 is 0. When t is greater than 0, then you are integrating past this delta function, then you get a 1. Okay. So that you get a unit state function. And as I say, you can also think this as the definition of delta function. It's something that's 0 everywhere and infinitely high 0. And when you integrate past it, it gives you a 1. Okay? That's delta function. Or unit impulse function. Okay. And okay, and derivative. So if you just reverse this relationship, then you get that the delta function is the derivative of your unit state function. You can just run the. You can just get this by applying calculus on this relationship, because the inverse of integration is derivation. Okay. And also something we didn't quite say is this k times delta function. Okay. So it's kind of ill-defined, because now you have some number, finite number k times your delta function, and then you have infinite height times k is still infinite. What's the difference? The difference is if you integrate over this, but it's still well-defined, kind of well-defined, because it's defined through this integration relationship. So if you integrate over this k times delta of t, then it gives you k instead of 1. Okay. So when we have a delta function here, this height is kind of funny, but it's a scale of infinity. So you can have a scale of 1 unit of infinite and a k unit of infinite. Although it should not make sense, but it's well defined in this integration sense. So you integrate this over this, you get 1, and you integrate over this, you get k. And you can even have a negative number here. You can have a -1 arrow pointing down here, and when you integrate over it, you get -1. And if you want to be want to think about this carefully, then you think about you are doing the limit of different this delta triangle. So say if you have k times k times delta here, then you actually you are taking a limit of k over triangle to infinity, to delta to 0. Okay. Okay. So the height will be k times triangle here, if you have k times delta. Any question? Not? Then yeah. Oh, okay. Then let's finish relationship. So yeah, just like in the discrete case, we can also do a change of variable on this running integral relationship and get rid of a t from here. So you change from tau to sigma equal to t minus tau. Now you are integrating over, so let's skip the math detail. You can check. I should not make a mistake here. And anyway, the integral will be 0 to infinity delta of t minus theta, t minus sigma d sigma. And you can look at this as the integration of it's the integration of sigma from 0 to infinity, but now you are placing your delta at a different location. So t minus sigma, deep down t. It's a little complicated. But for t greater than 0, this t minus sigma will be placed inside this 0 to sigma thing. So if we want to look at this as a variable sigma, I guess delta function is an even function. So delta of t minus sigma is the same as, so for this thing, oh wait, what happened? Excuse me? Wait, it's only on there, why? Okay. Anyway, so what I want to say is this is delta of t minus sigma. Oh, that's not sigma. Delta of t minus sigma is same as delta of sigma minus t. Not this. T minus sigma equal to delta of sigma minus t, I think. Yeah, because it's basically a delta, basically a even function. Okay. Because you look at this thing, okay, so this is not quite even, but when you take the time reversal, so you shift this to like here, and the difference goes to 0 when you take the triangle to 0. So that's fine. And okay, so delta of t minus sigma equal to delta of sigma minus t, and you look at sigma minus t. Then yeah, then when t bigger than 0 is in this 0 to infinity interval. Okay. But here you don't have the very nice interpretation of, I guess, the very straightforward interpretation of step function is just a whole bunch of delta function placing together, because it's a whole bunch of infinity and it's weird. But mathematically, you can check out this is true, what's going on. Okay. Anyway, question? Not? And let's go to the sampling property or shifting property of the continuous time impulse function. And well, if you just say the result, it's the same thing. So you multiply your whatever signal with the delta function, then we'll pick out x0 times your delta function. And you can also shift this around, so you have your x of t times your delta function. And shift to t0, then you pick up x of t0. And you can intuitively think about this is multiplying your whatever function with this very narrow rectangular. And when your rectangular get narrower and narrower, then the change of your x signal inside the rectangular become smaller and smaller. So it looks like a constant function times this rectangular, and the constant function height is your x of 0. Okay. Yeah. Because once again, the delta function don't care about any value outside of x at 0. So it's just x over 0 times your delta function. Okay. And yeah, here are the equations once again. The sampling property. X over t times delta of t equal to x over 0 times delta of t. And x over t times delta t minus t0 equal to x over t0 times delta t minus t0. And here is an example of analysis related to unit step function and the delta function. And it just show you that if you have a function that kind of look like this, so this is like a combination of unit step function. You have constant 0, then you shift to constant 2, then constant -1, then constant 1. And our question is what happens when you take a derivative of this thing. Okay. So if you just take a calculus class, it will say the derivative is 0 everywhere but undefined on this discontinuity. But now we have some way to describe the differentiation of discontinuity, right? Because it's like what happens when you take a derivative of the unit step function. And you should get the delta function. And even more, the delta function, the height of the delta function should be proportional to the discontinuity you get. So here you jump from 0 to 2. So you should have 2 times delta function at t equal to 1. And at this point, you jump from 2 to -1. So you should have a -3 delta function. So those are all infinity, but infinity times 2 and times 3. And another infinity times 2 here, because we jump from -1 to 1. Okay. Yeah. So that's basically this example. You have this constant function with 3 discontinuity, and when you differentiation, you get 3 delta function. And okay, so as a word of text, we can skip again. And we can also run this reverse, and so it's not much better. But anyway, so we think the derivative of this signal is this 3 impulse signal, and we can try to integrate it back, and we'll actually see the signal. So if we integrate from -infinity, then it keeps going 0, 0, 0, 0, 0. And then when you hit this delta function, you will jump +2 because you integrating over 2 times the delta function and get +2. So you jump to 2, then you integrate through this -3 jump. You will fall back to this -1. Then you integrate over and still stay constant. Then you integrate this over this +2 delta function. Then your value get +2. So that's just an example showing that the delta function is the differentiation of unit step function, or this discontinuity, and the unit step function is the integration of delta function. That's something we will keep using throughout the whole class. And here are the more mathematical solution. So you can, if you try hard enough, you can write this function as a very algebraic expression of 3 unit step function. So you have a unit step function starting from this t equal to 1, and another unit step function starting at this t equal to 2, and another unit step function starting at t equal to 4. And then you take you take a derivative of this, then you get 3 delta function. Okay. And yeah, then you can integrate it back, and you will get this unit step function. And constant is actually equal to 0. Yeah, because it's 0 here. Okay. Any question on the example? None. Okay, we have 5 minutes. Okay, so we will teach something very easy about our system. Not, then a little short on time, but anyway, something about system. So as we said at the beginning of this course, a system is something that transforms your input signal to output signal. And there are a lot of examples. And in this course, we'll consider a system that when you have a continuous time input, it gives you continuous time output. And when you have discrete time input, it gives you discrete time output. Okay? So it's nothing too special, just saying we won't change the discrete and the continuous time when we are going through a system. And we have some example of a system. So for example, we have a RC circuit. So this is probably more familiar with for those coming from electrical engineering. But anyway, you have a system that has some resistance and capacitance. And we are thinking that we are driving it with some voltage. Then we'll get some output voltage on your capacitor. And you can solve the differential equation, and you see that your input voltage and the output voltage are related to this relationship. So the VC dt and VC over RC equal to 1 over RC times your input. Okay. And here you see that the relationship between input and output can be something pretty complicated. It's a differential equation. So if you think of output is y and the input is x, then you have dy dt plus some constant a times yt equal to b times x of t. So this is one of the system we can see. And as we say, we express system in kind of funny way. So we never give you a name to a system, but we'll say system is x of t to y of t, and we'll write down some relationship between x and y. So that's usually how we define a system, and yeah, it's a little confusing, but that's the notation we use. And here we have another system that's maybe easier to solve, but have a different property. That's balancing a bank account. So let's say the x of t is the money you deposit in the nth month. And the output signal will be the total number of money you have in your account at some month. And also you have interest rate of 1% each month. Then once again we write down the relationship between output and input. Then you find out that your total amount will be whatever you had, and times your 1% interest rate, then plus how much you deposit into it. Okay. So yeah, so this is the relationship. So y of n equal to 1.011 y of n minus 1 plus x of n. And you see that this is different from the example before, because now this system has memory. So this thing actually depends on all the previous months. It's not just the output is not just dependent on the input of the current month. Okay. So the system can do this. And then we have seen this example, so we can also have a 6gun of a car, motion of a car. So you have input force, then you have output velocity, and etc. Then okay, so also something not too much right now, and this is something we are going to do calculation later, but for now it's just something to show. Is that we will express our system as those blocks, and we will thinking about how to piece together those blocks to do things we want. So yeah, so a system is something that you put input, then you can get output. So input through this block get some output signal, and we can actually interconnect those blocks. So like you can have a serial cascade of the system. So you have input to system 1, get some output, then put the output to another system 2, get another output. And you can also have a parallel interconnection. So if an input, then you can copy it to copy, then pass them through two different systems, and add together the two signals and get your output. Okay. And you can even have this very complicated system where you have a serial and parallel in different things, and even feedback things. Okay. But for now, it's just a show concept. I don't think we have calculation yet. And we're on time, so next Friday we'll go through those properties. And yeah, so we'll have a short homework, and see you next Friday. Yeah.
这周的作业是要怎么交？
那个可以交到助教的办公室外面，应该会有盒子，或是你直接想办法 email 给助教的。对。哦，可以。
一个就是CT 它的图形是会连续的。
CT 的什么 CT？
就是
CT 什么
？Continuous time 里面的那个，它上面图形一定是连续的。
一定是连续的吗？
就每个
你说 signal 吗？不见得是连续的。
不见得是连续，但都一定要有定义，对不对？
好像也不见得，有时候会很奇怪。像是我们会有这 U of t， 就是在零的时候，有时候会不太有定义，所以其实我们会考虑一些比较奇怪的 signal。
我是想说，如果像这样子零跟 delta 这两个点，理论上它应该是不能微分，所以可能它就没有定义，那这样子会是一个 CT 的数，或是一个 CT 的这样的。
我们说 continuous time， 你说它不是 continuous signal 是不是？
如果你带零跟 delta 进去，它就没有值。
对啊，但是不太影响，对啊，还是 CT 这样。
所以它不一定要有值。
对，不一定。然后，对啊，我们比较没有 rigorous， 就因为我们其实像我们还用这delta武器嘛，它就连方旋同时，它这个零的地方就无限大的，我还是用它。
那时候在常规听到的时候好像不太一样，是也有介绍这样的方式。
你们怎么定的？应该差不多吧。只是你们可能会有介绍一些说这个东西可以是什么任意形状、其实都没差之类的事情。对啊。
那时候好像没有分连续跟 discrete 去看这个函数。
连续跟 discrete
就是它是两个。
这个都是连续的。都是 continuous time。等一下，我先把这个。